Okay. Anybody have any questions about the homework or anything we talked about last time? Yeah.
Number 4 was the one where you had the object falling. Do you refer to the ground?
You don't have it with you, do you? I don't remember the problem.
I just described the problem.
Okay.
You have an object at height h, and falling, free fall on the ground.
Yep.
And you define time halfway down.
Oh, yeah, right. Okay.
Yeah, it refers to the variables that we refer to as.
Oh, so what's G? Is that what you're asking? G is 9.81 meters per second squared. So that's the acceleration of gravity. So you're gonna set up the equation as P final is equal to P0 plus V0 TF, and then minus 1/2 G TF squared. You know, that's the version with that as the acceleration, and then go from there. Okay. And so your P final is going to be h over 2. Your P initial is going to be h. You'll go through that. The thing that's going to be, well, that you have to be careful about is for the first half of the drop, that initial velocity is 0, right, because it's being dropped. For the second part of the flight, that initial velocity is something, and you have to figure out what that is. You know, for the second half of the flight, it's already moving, so you have to calculate that velocity. Okay? Any other questions? All right. So we've been talking about, so last time we started talking about vectors. And we started talking about, we talked about what a vector is geometrically and talked about adding vectors geometrically. You know, you can do it just sort of graphically on paper. If you use a straight edge and a ruler and did it carefully, you could exactly calculate the vectors that you get from adding two vectors together or multiplying a vector by a number, by a scalar. And so now what we're going to be talking about is, okay, so first we did thinking about vectors graphically. Done with that. And now we're moving on to doing calculations using components. So in a given coordinate system, so let's say your coordinate system is this, and I'll draw the negative x and negative y axes. And let's say that the vector we're interested in calculating is this. Sorry, let me use a different color for that. So that green, we'll call that the vector v. And to indicate that a variable is a vector, you put an arrow over it. So that's the vector v. And if this vector v has a length of L, then the components of this vector, to calculate these components, first figure out the angle theta that you get from going counterclockwise from the positive x-axis to the vector. In order to do it this way, the vector has to be, so the vector's tail has to be at the origin. You can move vectors around, so you can, if it's vectors, a vector only is a magnitude and a direction. So there's no, so you can pick up the vector and move its tail to the origin, and as long as you don't change the direction or the length, it doesn't change anything about it. And so that angle would be this in this case. So start at the positive x-axis, go counterclockwise to the vector. And then the vector components are the length times the cosine of that angle theta, length times the sine of that angle theta. And you can also equivalently write it as that x component, that I with the fancy hat over the top, says that's an object pointing in the x direction, and a j with a hat on top says pointing in the y direction. So these are two equivalent ways to write the components of that vector. Okay. All right, so let's say that we have a vector, so there's the horizontal, and let's say that we have a vector that makes an angle of 30 degrees with the horizontal that way. Let's figure out what the components are in this coordinate system, this coordinate system, and this coordinate system, where this angle is 20 degrees. Okay, so take a minute and start by doing part A, and then I'll do that. We'll make sure that we're all on the right track, and then we'll go on to B and C. So see if you can think through that and talk to each other about it, compare answers. You're like, you're dumb. Okay, so for part A, there's the coordinate system. Here's the vector. This angle is 30 degrees, so our angle theta is all the way around like that. And so the vector components are the length, 10, times the cosine of 330, 10 times the sine of 330. Like I said, you could also call that negative 30 degrees, and then that's 10 times the cosine of negative 30, 10 times the sine of negative 30. And you get 8.66, negative 5. You can also write that with the other notation, 8.66 times fancy I. Look at that I. Thinks he looks so fancy in his little hat. And then minus 5 times fancy J. Okay, those mean the same thing. Any questions about that? Okay, now do part B. So same vector, new coordinate system. So you're going to get different components.
please go so we can just see reason?
Okay, so for B, we have the x-axis up, the y-axis to the left. The vector, though, doesn't change, okay? That vector, it lives where it lives in space, and our choice of coordinate system doesn't have anything to do with that. So the vector is still like this. Okay, and the angle between that vector and this dotted line is still 30 degrees. Okay, so what's the angle in this case? I guess I'll draw a continuation of the, so there's the negative x-axis. So what's the angle theta? Well, it's 90, 180, and then one way you can think of it is, you know that this angle is 30 degrees, right? So you can think of this angle as 90, 180. It would be 270 if it made it all the way there, but it doesn't quite. So 270 minus 30. Okay, so 240. Or you could go the other direction and go negative 90 and another negative 30, so negative 120. And sine and cosine of 240 is the same thing as sine and cosine of negative 120. So the vector is, the components are 10 times the cosine of 240, 10 times the sine of 240, and so you get negative 8.66. Wait, no. You get negative 5 and then negative 8.66. And you can write that in that snooty IJ notation. Negative 5I minus 8.66J. Every time I see them in those hats, I just hate them more. Any questions about that one? Okay. C. All right, so this coordinate system is this way. Where this is the horizontal, and this angle is 20 degrees, and the vector is this direction, where this angle is 30 degrees, so what's the angle theta for this one? Yeah, so it's, you can go negative 50 or you can go positive 310. So you get 10 times cosine of 310, 10 times sine of 310, which is, I think that is going to be the y is going to be negative 7.66, right? What's the x? I'm blanking on that one. What? Ah, okay, thank you. So positive 6.43. And then You can also write that as 6.43 times I minus 7.66 times j. Any question about problems like that? How to get those in? So remember that the components of the vector change depending on what your coordinate system is. In a way, it can be a little unsatisfying just putting angles into your calculator and getting sine and cosine. So I want to tell you, point out an equivalence that'll help you kind of sanity check your answers, at least make sure that the signs are right on the components. You either have the right plus, minus, you have plus minus or minus minus or whatever. So notice that calculating vector components is equivalent to putting the vector's tail at the origin and second, calculating the coordinates of the vector's head. Okay, so in other words, like if you, let's look at the first example. It's in like the standard orientation of coordinate systems that we're most used to. If you put the tail of the vector at the origin of the coordinate system, the components are the same thing as the coordinates of that point right there. Okay? So what quadrant is that point in? One, two, three, fourth quadrant. So what should be the signs of those coordinates? What's the x coordinate? Is it positive or negative? Positive. Y coordinate? Negative. And that matches with the components. Okay? So you can always use that to eyeball whether your components make sense. One thing that's helpful for is, since I said, you're going to have classes where your calculators are in radians, classes where your calculators are in degrees. This will catch that a lot of the time because, if your calculator's in degrees and you put in negative 30, if your calculator's in radians and you put in negative 30, you're going to get some wacky answer. Most, chances are it's going to be in the wrong quadrant, and you can, find it that way. Okay, so let's do a couple of examples. So all you have to do is give me the signs of the components. And I'll just use this standard orientation for the coordinate system. Okay? So first, that vector. What are the signs of the components? Both positive x, and so there's the coordinate system. So you have positive, positive, or positive I and positive j. How about that one? What are the signs of the components of that one? Negative x, positive y. Sometimes it's hard for me to tell the difference between when you're lost and when you're bored. Can you tell me that much? Who's lost and who's bored? A little of both?
You can ask them to give you thumbs, like this means they're with you, this means they're not with
Okay.
you, this means they don't even know if they're with you.
Yeah, they're not paying it. They're thinking about something else. So, yeah, give me the thumbs. Everyone? Okay. So, this one should be negative x, positive y. How about this one? Straight horizontal, pointing to the left. That's right. So that should be a negative x, 0y. How about this one? X component, is it positive or negative? Positive, and then y component? Negative. Yep, good. All right. Now, once you have vectors written in components, let's go back to remember the two calculation types that we did graphically with vectors. We talked about adding two vectors and multiplying a vector by a constant. So let's go back to this algebraic vector math with components. And here's how it works. If you're adding the vector AB to the vector CD, the resultant vector is equal to A plus C, B plus D. And that way of doing addition of components is exactly equivalent to doing that graphical addition that we talked about last time. So, for example, if you have 1, 6 plus negative 5, negative 2, the resultant vector is negative 4, positive 4. And so that vector looks something like, if this is your coordinate system, something like that. And then multiplying a vector by a scalar. So this is vector addition. Now multiply a vector by a scalar. If you have a vector AB and you're multiplying it by the number C, the scalar C, the result is CA for the X component and CB for the Y component. So, for example, if you have negative 20 times 2, 4, the resultant vector is negative 40 negative 80. And so it is something like this. Okay. So let's do a couple examples where we can see that these two ways of doing algebraic vector math are equivalent. Because it seems a little surprising in a way that they're like, I think it doesn't jump right out at you why those are the same thing. But you need to be comfortable with both of these ideas, both of these ways of doing vector math. So let's say that we have, we want to take negative 2 times the vector that has a magnitude of 5 and makes an angle of 45 degrees with the horizontal. And let's use that same coordinate system, the one that we're most used to. So do this calculation graphically and using components. And then we'll compare the two and make sure they make sense. Okay, so graphically, the 2 means that you have to go twice that length. And the negative 1 means that you have to switch the direction. So the vector is something like that. And so what should be the sign of the x component when we do it in components?
Negative.
Yep. And the y component? Negative, exactly. And then using components, what is the angle theta that we need to use? So the vector is we're given that this angle is 45 degrees. Okay, so what's the counterclockwise angle from the positive x-axis to the vector? 45. So the components are 5 times the cosine of 45 degrees, 5 times the sine of 45 degrees. And so that's 3.535, 3.535. And now we're going to multiply that by negative 2. And you get negative 7.071, negative 7.071. And as far as we can tell, does that make sense with that? Yeah, I mean, both negative signs, this looks like it's, you know, it looks like the x and y components should be pretty similar, or, I mean, they're exactly the same actually, but we can tell that they should be close, and they are, so those match. So let's do one with addition. let's say that we have this vector with a length of 1, and we're adding it to this vector with a length of 2. So do that graphically. And with components. Okay, so graphically, you can do it in either order, but put the tail of one of them at the head of the other, and then the resultant goes from the free tail to the free head. So if this is the resultant vector, the sum, what do we expect to be the sign of the x component? Negative x component. What do we expect to be the sign of the y component?
Negative.
Yep, so negative, negative. And then do you have a feel for which of those components would be bigger in magnitude? The y component will be bigger. So that's what we expect when we do the calculation with components. All right, so now using components, what are the components of, okay, well, there's kind of two ways you can think of this. So there's the vector. Here's the coordinate system. So what would be the angle if you're going to do it using cosine and sine for this vector? 180. But you can also just use the fact that this is equivalent to just giving the coordinates of the head. And so then you get the same thing by just recognizing that this is lying on the negative x axis. And so that vector has components of negative 1, 0. Okay. And then the second vector is this. What's the angle for this one if you're using cosine and sine? 270 or negative 90. But again, you can just recognize that we're talking about the coordinates of that point. That's a length of 2 away from the origin in the negative y direction, so this is just going to be 0, negative 2. And so when you do this addition, you get negative 1, 0, plus 0, negative 2 is equal to negative 1, negative 2, and that matches just what we expected from doing the graphical approach. Okay, any questions about that? All right, there's one more algebraic calculation we need to do. Using vector components. And that is calculating the magnitude of a vector. And the magnitude, remember, is the length of the vector. Okay, so if you have a vector, so let's say our vector v is vx, vy. No, let's call it just ab. Okay, so the x component is a, the y component is b. Or a times fancy I plus b times fancy j. The magnitude of that vector, and you write that as an absolute value of the vector. That's how you represent a magnitude. So vector v, absolute value, means the length of that vector, is equal to a squared plus b squared square root. And if you think about it, it makes sense because it's just the Pythagorean theorem. If this is your vector, and you want to figure out that length, and your components are this and this. This is A, this is B, this is a right angle. And so you know that the hypotenuse length of a right triangle is equal to the square root of the squares of the legs. Okay, and so that's where this magnitude comes from. So now we're done talking about algebraic calculations, but we have to do a couple of calculus calculations with vectors. So now we're going on to calculus with vector components. There's no real equivalent for doing calculus graphically with vectors. So for derivatives, and integrals, and this doesn't mean much to us now, but if you take later dynamics classes and stuff, this will be a significant thing. This only works for non-rotating coordinate systems. For now, I mean, your reaction to that should be, why would you ever want your coordinate system to be rotating? We don't want it to be. But there are cases of complicated calculations where you're required to have a rotating coordinate system, and then you'll have to treat this stuff a little bit differently. But if your coordinate system isn't rotating, the derivatives of a vector f of t, g of t are just equal to the derivative of f, that's the x component, and then the derivative of y, that's derivative of g is the y component. So you just do those two independently. And it works the same with integrals. So the integral of a vector f of t, g of t, dt is the integral of f with respect to t for the x component, and the integral of g for the y component. Okay, so the x and y components are independent of each other. So as an example, if you have a vector v, it's a function of time, and it's equal to 5t t squared, let's calculate the time derivative of v and the integral of v with respect to time. Okay, so for the derivative, what's the x component of v dot? Just 5, yep. And then what's the y component of v dot? 2t, yep, exactly. And for the integral, so there's our v. What's the x component? Yep, 5 halves t squared, and then don't forget the constant of integration. So we'll call that C1. And what's the y component? Yep. So t to the third over 3 plus C2. Okay, so there's one important thing to notice here. In all of these calculations, involving components, using the components, the calculation of the x component and the calculation of the y component can be done completely independently. Okay. Totally independently. Exclamation! Okay. Is everybody over the shock of that one? Okay, that's going to be a useful thing for because we're gonna come up with these vector equations, and this says that those equations can be done. So a vector equation with two components is going to be able to be broken up into two regular, scalar equations that we can solve separately, an x equation and a y equation. That's going to be a useful thing. All right, so now that we're done with all the, so we're done talking about what vectors are and how to do calculations. So now we have to talk about, the reason we introduced these is that in 2 dimensions and in 3 dimensions, all of those kinematic quantities that we described along a line that were signed scalars before are now vector quantities. So now we have to define 2-dimensional position, velocity, and acceleration in terms of vectors. And if you compare the way I'm going to introduce these as vectors to the way that I did it for motion along a line, you'll see that everything follows very closely. There's equivalence for everything that I did for defining these quantities along a line. There's equivalence now in 2D as vectors. So let's first talk about the position vector. So now we have an object moving around in 2D. It can do all this, you know. It's not confined to a line anymore. Do you remember when we talked about position along a line, what was required before we could assign a number to the position? There were two things that we had to choose before we could specify a position value for something that's out there in space. Yep. So in 1D, so needed to specify the position. In 1D, or I guess along a line, we had to specify the 0 position and the positive direction. There are equivalents to those in 2D that maybe you could guess based on our discussion of vectors so far. What do you think is going to be our, in 2D is going to be our equivalent to choosing a 0 position? Exactly, yep. So you have to choose an origin location. And then in 2D, what do you think is going to be our equivalent to choosing the positive direction?
Choosing quadrant 1.
Yeah, let's call it choosing the axis orientation. But we have to choose the way that the coordinate system is oriented. Once you do that, so once you make these two choices, and let me go up here, and so actually a lot of times people call these two choices a single thing. They just say choosing a coordinate system. Choosing a coordinate system means choosing where the origin is and choosing how the axes are oriented. But once you make these two choices, here's your coordinate system. Here's your object moving around in space. And the position vector is the vector going from the origin to the object. So there's your position vector. So the position vector P is a vector from the origin to the object, to the particle. For motion along a line, what did we have for units? Well, it's a measure of length. So there are always going to be units of length. What are the SI units for length? Meters. And in 2D, it's exactly the same. So each component just has units of meters. So after I talked about it with motion along a line, do you remember what did I talk about as the next choice we had to make so that we could specify the position as a function of time, which was eventually what we were trying to get to? That's right. We had to make so to specify, let's say, to determine the position as a function of time, had to specify a third thing. Like physical instant corresponding to time equals 0. What you're doing essentially, you're choosing an instant to turn on the stopwatch. Time isn't changed in 2 dimensions, and so this stays exactly the same. So this choice remains the same in 2D. So once you've chosen an origin location, like a physical location that you're going to call the origin of your coordinate system, coordinate system axis directions, and a time 0 instant, you can determine the position vector as a function of time. So, for example, you might have that the position vector is equal to 5t negative t squared. If you're given something like that, it means all those choices, those 3 choices, have already been made for you. With motion along a line, it went pretty naturally from coming up with a function of time for the position to plotting out a position versus time graph. Now one graph won't do it because we have those 2 separate components. So to plot position versus time, you have to plot those 2 components separately. And you don't see that as often as you do in one-dimensional motion. So you plot the x position versus time and the y position versus time separately. So in this example above, if this is the graph of the x position versus time, it would follow that function. And if this is the y position versus time, it would be like that parabola. Okay. So after we defined the position in one-dimensional motion, what was the next quantity we defined? So we're doing position, velocity, and acceleration, and the next thing we defined was instantaneous velocity, and what was the relationship in one dimension between position and velocity? Yeah, that's right, the time derivative of position. So now we're going on to the instantaneous velocity vector. And just following exactly analogously to the relationship between positions, now the velocity vector as a function of time is equal to the derivative of the position vector with respect to time. If you're looking at graphs of the x position versus time and the y position versus time. So on the graph of the x position versus time, the x component of velocity is the slope of a tangent line. And on a graph of the y position versus time, the y component of the velocity is the slope of the tangent line. And the units of velocity, again, don't change. They have to be length over time. And so in SI units, that's meters per second. Okay, so as an example, if you have a position function, position is a function of time that's equal to 10 times cosine of 2t, 10 times sine of 2t. With these angles in radians. What's the velocity vector as a function of time? And second, what's the velocity vector when time is equal to 3 seconds? Okay. Take a few minutes and work through that one. Anybody want more time to think about it? So, to calculate the velocity as a function of time, you take that time derivative. So velocity as a function of t is, you have to use the chain rule. You get negative 20 times the sine of 2t and 20 times the cosine of 2t. And then for b, just plug in 3 seconds in for time. So you have negative 20 times the sine of 6 radians, positive 20 times the cosine of 6 radians, and you get 5.59, 19.20, and these are meters per second. Okay, so let's think a little bit about what this is telling us about this motion. If this is the position function, does anyone have a feel for what that motion is as time goes forward? What's that object doing? Yep, it's a circular path. So if we're looking at, so now we're not looking at a graph of anything versus time, we're just looking at its motion in the xy plane, and it's starting out over here, and it's going through this circular path. Okay, where the radius of this circle is 10. At time equals 3 seconds, where is it on this path? Okay, it's going this direction, by the way. So where is it on this path at time equals 3 seconds? Well, it's at 6 radians. So a full rotation would be 6.28 radians. So it's almost back to, it's somewhere like this. Okay, this is at time equals 3 seconds. So what is that velocity? What do you think is going on with that velocity vector? How does that relate to this path? Well, you can see it's going in the positive x direction a little bit, mostly in the positive y direction. And so that velocity vector is tangent to that path. So at any instant, the velocity vector is tangent to the path. Okay, so that leads to this sort of interpretation of what the velocity vector tells you, the meaning of velocity. So I gave a description like this when we were talking about motion along a line. Do you remember what I said about velocity in 1D? So I broke it down into two things, like an absolute value, and what does that give you in one dimension? The speed, and then it's either positive or negative, and what does that tell you? The direction that it's moving. And so in 2D it's similar. There's a magnitude. That's the length of the vector. And that gives you the instantaneous speed. And then, of course, there's also a direction of the motion, the vector direction. That's the direction of motion, and it's tangent to the path. It's always tangent to the path. which is what we saw in this example. Okay. So the instantaneous direction of motion is always tangent to whatever path it's following. Okay, let's do another example. So let's say that you're given an object's position vector that's equal to 10t 5t squared. Sketch the path of the particle on the xy plane. Then calculate the velocity vector as a function of time. And then show the velocity vector on your sketched graph at time equals 1 second. Okay, take a few minutes and do that. Do this and then we'll call it a day. All right, so this path is going to look like a parabola, concave up. When time is equal to 1 second, I don't know, let's say that's here. The velocity vector as a function of time is the time derivatives of the component, so that's 10 and then 10t. So when time is equal to 1 second, you have a velocity vector of 10, 10. And so that's tangent to the graph at that point. So at that instant, that's the direction that the object's moving. Can anybody tell me what the speed of that object is at that instant? So this is 10 meters per second, 10 meters per second.
I don't, can't tell you, but I have a question.
Yeah.
So how is it tangent to the graph at 10, 10 if the function p of t isn't on the point 10, 10?
So remember that vectors are only a magnitude and a direction. They don't have a location.
So it's more that that's the slope of the vector?
That's right. So that gives you the magnitude and the direction of the vector. I just positioned it on the graph so that you could see that it was tangent. Okay? Does that make sense? Okay, so how would you calculate? Yep. How did I what?
Because you have to do the 10t is the function of x.
Yeah. So, well, you could just plot points. But the way, okay, yeah. Think of it as, here's a good way to think of it. Think of it as 10t is equal to the x value. And so the y value is equal to, what's the relationship between the y value and the x value.
Like x squared over 20.
Yeah, x squared, is that right? X squared, yeah, very good. X squared over 20. So you can think of it like that. All the t is doing in there is telling you how far along that curve you are at a given instant.
I don't think that's right.
You don't?
I think it should be x over 10, and that's squared, and then that's times 5.
I think that's the same thing. I think that comes out the same. Okay, so this is the velocity vector. What's the speed? Remember how to calculate the speed from the velocity vector? So the speed is the length of that vector, the magnitude of that vector. And so you use the Pythagorean theorem. And so the speed is 10 squared plus 10 squared square root, which is, I don't know what that is, square root of 200. What? Thanks. 14.14 meters per second. Okay? Any questions about that? Okay, that's it. So remember, there's a quiz tomorrow. And yes, that's all.